Welcome. I'm Ken Melville, and my relationship to Raffaele Ferrari being here is that I was chair of the Cody Award committee that this year awarded Raffaele the Cody Award, and the other Scripps participants in that committee were Mark Oman and Steve Candy, and we had also three colleagues from other institutions assisting in the decision. I think the official award is being made tomorrow by Margaret, so I shouldn't go into that too much. But each Cody Award winner is asked to present two lectures, one for the public, which will be presented tomorrow here in the same space, I believe at the same time, and a second lecture, a so-called technical lecture, for people with direct interest in the field or who would like to learn something about it. Raffaele Ferrari is well known to his friends as Ruff, friends and colleagues as Ruff. He's the Bean Kerr Professor of Physical Oceanography at MIT and the director of the program in Atmospheres, Ocean and Climate. After degrees in physics and fluid mechanics in Torino, he became a student at Scripps in the 90s, and under the supervision of Dan Rudnick and Bill Young, graduated in 2000. Following that, he spent 2 years at Woods Hole, and then was appointed assistant professor at MIT in 2002. He rapidly rose through the ranks. A rise that was helped by winning the Pfaffenhoff Award for early career physical oceanographers back in 2007, and he was appointed a full professor at MIT in 2009. Raf has had a great influence on the field of physical oceanography in his relatively young career, although it's becoming a middling career, I think, by now. The grey hair is accumulating, and he has become, I think, one of the leaders in his generation of physical oceanography, the sort of person that people go to when they want to get help answering their questions. So it's a great pleasure for me to introduce Raf today, and he's going to be talking about an old topic that was introduced by Walter 50 years ago on abyssal recipes. Thanks, Raf.
Okay, thank you very much for the introduction, and I must say that I still feel very awkward receiving a prize in front of, people who were my teacher, my scientific heroes. I still feel out of place. A lot of people have achieved much more in their career than I did, but I can blame it on the committee. I didn't have anything to do with it. Instead, what I want to discuss today in this lecture is work that we've done recently, I have to be careful, on trying to improve on what has been the first paper that was exposed to in oceanography, and this is for real. I think Mary Hendershot is here in the audience. I took Introduction to Observational Oceanography with him, and in one of the first lectures we were assigned Abyssal Recipes, this paper, written by Walter Monk. And at the time, I found it both refreshing and puzzling. I was coming from physics. This seemed too simple a paper to deserve all the attention it was getting, because you're coming from physics where if you don't get at least 6 pages of really dense equation, it's not something that have any profound impact. And at the same time, he was making very fundamental statement about the state of the ocean. What the paper was really trying to address is how does abyssal waters come back to the ocean surface, and with very simple and clear arguments, making a full picture of what the dynamics of the problem should be. So what I want to do today is to revisit that original paper in light of observations that have accumulated in particular over the last 20 years that cast some doubts about some of the fundamental assumptions and asked for some slight revision of what was that original picture. And this is work I've done in collaboration with Ali Mashayek at a postdoc working with me at MIT and Trevor McDougall at the University of Sydney. Again, starting back, so what I want to do is to improve on an abyssal recipe. You all know that Walter Munk was born in Austria. He's an American citizen. Instead, you must have guessed, if you didn't already know, that I'm Italian from my accent. So if nothing else, you should give me some credit. I should be able, as an Italian, to improve on a recipe that was generated by an Austrian American. So first, let's review what is the basic idea behind the abyssal recipe in its original formulation.
Question. Are you willing to change the second S to an N?
Second, abysmal. Well, we'll see by the end of the talk, you decide. So what was the original statement? And I think what is most important, what was the question that Walters was trying to address at that point? And this goes back to work that was started a bit earlier even than abyssal recipe itself, from Henry Stommel. What both Stommel and Munk were trying to understand or explain were two fundamental aspects of the ocean's mean structure. The first one was the fact that the ocean is a stably stratified fluid. This is a section of the Pacific Ocean. This is depth, and this is latitude. The equator is somewhere here in the middle. This is the South Pole and the North Pole. What you see in colors is the density of the ocean, where it's red, it means light, and when it's dense, it's green. So the ocean is a set of layers that are becoming progressively denser towards the bottom. So the ocean is really stably stratified, meaning it's like a set of pancakes sitting on top of each other. This is a section that was collected as part of the World Ocean Circulation Experiment in the Pacific. I think this particular section by Lynn Talley, if she's here, I don't know. So the first question is, why is the ocean stably stratified? And the second puzzle in this story was the fact that also as part of this World Ocean Circulation Experiment, people had collected a section in the global oceans through the various oceans, Atlantic, Pacific, and Indian. And Lampkin and Spear in particular in 2007 were able to produce a map like this one. This is now latitude from the South Pole to the North Pole, and this is depth, but now we're looking at the zonally average velocity field of the ocean. In particular, we're looking at stream function. In a zonally average sense, what is the circulation of the water masses? And if you do this exercise, you find that the ocean is really characterized by two overturning stream function, or two big circulation. One is this upper one. It's associated with sinking of waters primarily in the North Atlantic, and then this water comes back all the way to the Southern Ocean to fall back into a clockwise circulation. This circulation requires very little diabatic transformation in the interior. This was one of the main results of the World Ocean Circulation Experiment. So you can just assume that the circulation is along those density layers that I've shown you before. However, there is a second deeper circulation associated with water sinking all the way to the ocean bottom around Antarctica. These waters instead flow all the way to the ocean bottom, and then you see that they fold on it themselves. The flow of this water folds on itself until they come back into the Southern Ocean. It's guaranteed that this water have to cross density surface in order to come back to the ocean surface. So the question was, we had to explain two aspects. The first one, the ocean is stably stratified, and there is an overturning circulation, as it has been called since, that crosses this density surface. So it was answering this question, and how do you put together a circulation that can achieve transport across density surface. I keep insisting that the circulation is crossing this density surface because that made the problem quite challenging. We already knew at the time that large-scale currents, or even large-scale geostrophic eddies, as they've been called, the cyclone and anticyclones of the ocean, tend to be very effective at transporting property along density surfaces, but not quite as effective across density surface. So it was a puzzle that there is all this water that seems to happily rise across the ocean stratification. So starting from I guess Henry Stommel first proposed that probably the story was that there must be some mixing that allows water to rise across density surfaces. But then one has to ask the question, this was really Walter Munk's contribution, was coming to the point of, well, can we estimate what that turbulence is? What are these motions that allow the flow to come across density surface? And is there any observational evidence for a process of that kind actually happening in the ocean, or we're just thinking about the problem fundamentally incorrectly? And so this is the picture that came out of the seminal work of Walter Munk in the Abyssal recipe. He said, well, if we know that, if we want to posit that there is really all that water that from the abyss is rising towards the ocean surface, well, then we can write a pretty simple balance where we have vertical advection density, the density field. This is this water that is advecting density upwards, supposedly. And that has to be balanced by a diffusion of, let's say, heat. It's technically density, but heat is the primary component we're thinking about here. There must be diffusion of heat from the top of the ocean downward to allow this water is coming up to become lighter and rise as it's moving upward. So that balance had to hold, and he really used a simple formulation. It's just the Fickian law, where kappa T is the diffusivity that is allowing this water essentially to be warmed up by the diffusion of heat from the top of the ocean and getting lighter and rising through these density surfaces. In particular, if you assume that the upwelling of water is pretty uniform through the global ocean, so you assume this W is constant and this diapicnal diffusivity is constant, you can solve analytically this equation. The solution is just an exponential profile that is given here with an E-folding scale goes as diapicnal diffusivity over the vertical velocity. So the E-folding scale of that exponential profile is related to the two processes that you want to know about. What is the rate of upwelling of waters and what is the rate of diapicnal diffusion in the global ocean? Then what Walter did is that he could take just profile of density in the Pacific, and here we're talking about the abyssal circulation. Remember that we're really talking about this abyssal overturning where waters are clearly crossing density surfaces. So let's say that particularly in the paper, he used only profiles starting from 1,000 kilometers below the ocean surface. So we're looking at the temperature, the density profile, strictly speaking, below the ocean surface, 1,000 meters or below. You see, it has a quasi-exponential profile, so I can try to fit an exponential to it. I get a folding scale, and therefore I have an estimate of what is this ratio W over kappa rho, or kappa rho over W, this e-folding scale, directly from observations. One way just to summarize the work would be to say, well, now the next thing is I just got the ratio of this W over kappa. I don't know what either one really is, but already at the time, there was sufficient information to know at least what was the order of magnitude of this W, of the amount of upwelling, because after all this water that is coming up must be equal to the amount of water that is formed at high latitude and is sinking into the ocean interior. The amount of water formed at high latitude and sinking in the ocean interior is of order of 30 Sverdrup or so, but as an order of magnitude, that's the number 30 Sverdrup means 30 times 10 to the 6 meter cubed per second. If you assume that that sinking water is uniformly upwelling redistributed over the global ocean, you get that the W that can achieve that is of order of 10 to the minus 7 meters per second. So if you multiply this by the area of the ocean, you're going to get your 30 Sverdrup upwelling. So now, if you know something about the W, you can infer what the kappa is. And the kappa that came out of that argument was of the order of 10 to the minus 4 meters squared per second. There are people that have argued that we should really call this one monk, because this is a seminal number that came out of that work, that is really the amount of mixing that you need to close that budget. Now, the reason why this was so influential is that this 10 to the minus 4 was 3 orders of magnitude larger than the molecular diffusion of heat, 5 orders of magnitude larger than the molecular diffusion of salt. So that indeed confirmed the assumption that there must be some turbulence at play to bring that water back up, because the rate is much more efficient or much higher than just molecular mixing would be able to do it. It's the reason why you stir milk and coffee in order to accelerate the mixing of the two fluids. If you allow molecular diffusion to act, that would take much longer. So now the question is, what is the turbulence that is allowing that rate to be as large as what seems to be implied by this simple budget? And indeed, Walter Munk, at that point mostly with Chris Garrett, started researching on what kind of turbulence could really support that rate of mixing. And we're looking at the ocean interior. So the ocean, as I said, is a set of layers of different densities, or this can be thought about as a layer of different densities. And you can have waves at the interface between these different layers. So you can generate what are called internal gravity waves, much like surface gravity waves that exist at the interface between water and air. And indeed, over the 70s, people researched the existence of these gravity waves. There is a Garen-Bank spectrum that showed us the internal gravity waves are indeed quite pervasive in the ocean interior, where it's stratified all the way from the surface to the abyss. But in particular, what is interesting about internal gravity waves, and this is going to be an example we're going to look at in a second. This is a two-layer system. This is dense water, and this is light water. And this is an interface. Just saying, if I allow an internal gravity wave to exist at that interface, that gravity wave will generate changes in velocity between the two layers, the vertical shear, and that can go unstable, much like surface gravity wave can break. And what we're going to see is that if one of those waves does break, now this is the trickiest part, because I don't see it on the screen, okay. Now you see what happens when this gravity wave breaks. Now we dyed the color, these are the density or the temperature of these two water masses. You see all of a sudden you mix the fluids in between. So a gravity wave, an internal gravity wave that breaks can mix fluid across density surfaces, which is what we said was the key point on allowing this water to rise through the surface. This form of instability is called the Kelvin-Helmholtz instability. So the idea was that there is a very strong gravity wave field, and apparently this gravity wave field is large enough to allow, or gravity waves break often enough to allow some of the surface heat entering into the ocean from solar heating to propagate all the way into the ocean interior and allow this water to rise towards the surface. So up to here, everything seems to be good. There is a very self-consistent theory that has pointed out to the importance of these gravity waves and breaking of gravity waves being the turbulent process that allows waters to come back to the ocean surface. Now we're getting to what I call the conundrum. So what is the problem with that argument, or is there any problem with that argument? And I will contend that what has happened since, starting from the 80s and 90s, that people started looking at how do you generate these waves, and especially, now more importantly, where do they actually break? Because it's really the breaking of the waves that eventually matters. Just knowing where the wave field is not sufficient. It's like, we know the surface gravity waves exist everywhere in the ocean, but they mostly break on beaches. So it really matters that we find out what are the equivalent of beaches for the internal wave problem. And again, a lot of work, this largely done between, again, Scripps and Woodsall, pointed out that there are two main ways in which you can generate this gravity wave field. One is just by surface winds perturbing the free surface of the ocean and eventually radiating waves in the interior. While you generate a lot of waves that wave, the overwhelming evidence over years that has accumulated is that you don't generate much breaking gravity waves. Those gravity waves are not that strongly nonlinear. The other ways you can generate waves is to have instead motions that flow over bottom topography, which is uneven. So now if you have a current that moves up and down, it displaces this density surface and generates waves. Those tend to be much more nonlinear in the way you would define it as in GFD jargon. So they tend to be they're more likely to break close to where they are generated. And this way can be generated either by strong tidal flows, barotropic tides that slosh back and forth over ridges and seamount, or the equivalent of cyclonic and anticyclone, the equivalent of oceanographic equivalent of atmospheric cyclone and anticyclone that generate ocean motions all the way down to the bottom. And again, they generate gravity waves that do break there. So now the question was, well, if there are all these waves that break all the way to the ocean bottom, can we actually measure if there is mixing associated with them? And now the problem was that we're talking about really the ocean bottom on average is 4,000 meters below the surface, and you're asking to measure the results of a gravity wave breaking and the mix it generates. So that is happening all the way down to scale of centimeters. So it wasn't a trivial measurement to do. So this is work mostly done at Woodsall, where people design what is called now a high resolution vertical profiler. So you have a big float that sinks vertically into the ocean, and on the nose of this float, you have a shear sensor that measures any small displacement of the water column. It's just a piezoelectric element that every time there is a current that represents some turbulence that is being generated by one of these gravity wave breaking, and it gets deflected, and it tells you that there is a large velocity or a large shear in the water column. This could be left sinking all the way to the ocean bottom, and then it just would pop back up to the surface, and so you could finally go all the way to the deep ocean and measure vertical profiles of mixing. And this is the first paper that reports measurement of mixing rates. So now we're really looking at the result of a gravity wave breaking. And this is from the Brazil basin. It's in 1997. And this is now a seminal paper that is published by Polzin and collaborators, the Woodsall group. And what we're showing here is profile as a function of depth, or it's really height above the bottom. So this is the bottom here, you're moving above the bottom. And this is the intensity of mixing. It's really how much velocity you see at this small scale that represents the turbulent patch that is mixing. And you see that the profile is larger at the bottom and it decreases towards the surface. You should realize that this is a logarithmic scale. So there is close to an order of magnitude more mixing close to the ocean bottom and away from it. These are three different profiles on different regions with different topographic structure. But you see consistently as you go close to the bottom, mixing tends to be enhanced. In particular, if you have strongly sloping bottom, the effect seems to be even more pronounced here. We really are talking about 2 orders of magnitude enhancement. This is not true only in the Brazil basin. That was a place where there was a very strong barotropic tide, so it was essentially tidal generation and internal tides that seemed to break very close to the ocean bottom, because the result, this turbulence is really already talking about the aftermath of the breaking event. So now we can look instead in a different place. This is a more recent experiment that again uses HRP in Drake Passage. So we are in the Southern Ocean. That's a place where the barotropic tide is pretty weak, but now you have very strong geostrophic eddies that have the same effect. And again, if you look at epsilon, or the amount of kinetic energy at the ocean bottom at this small scale, it's again enhanced by orders of magnitude compared to the value that it has 3,000 meters above the bottom of the ocean. So consistently everywhere you look, if topography is sufficiently irregular, you tend to find strong enhancement of the turbulence very close to the ocean bottom that then decreases pretty rapidly with an e-folding scale of 500 meters or so. So that was the observational context. We don't have many examples. I mean, here I'm showing these 2 Drake passes, something I was involved in at least as part of the group. I didn't go out to sea. I can't take any credit for that, and I don't want to. And Brazil Basin was another example. There are very few other examples where we went all the way to the ocean bottom, but every time we go, that kind of pattern seems to emerge. So why is that an issue now? This, I would contend, is the observational context that asks us to revise a bit the original picture. And the way we have to revise it now, let's consider an idealized ocean. This is our bottom topography. This is a water parcel in this ocean that is now the real ocean. So you realize that the mixing tends to increase towards the ocean bottom. So this water parcel is sitting in the stratified ocean, so it has denser water below it and lighter water above it. And we said the mixing tends to be stronger towards the bottom than above it. So this water parcel tends to be mixed more efficiently with denser water than with the lighter waters above. So as a result of that mixing pattern, that water parcel is getting denser, not lighter. But if it gets denser, it's doing the opposite of what we were asking that water parcel to do. It's getting denser, therefore it starts sinking towards the ocean bottom, just because of the profile of mixing that we have observed. So now, the idea was that all this mixing in the ocean interior was warming waters up so that they could rise towards the surface, but because of the profile that has been measured, that implies that these waters would actually sink. That's true, except in one very special place. If I have a water parcel really sitting over the ocean bottom, this water parcel is not going to be mixed with anything below it. Turbulence can only mix waters. There is a non-normal velocity boundary condition eventually in the ocean bottom itself. So this water parcel is only mixed with waters above it, so it tends to get lighter. If it gets lighter, then it can rise, and especially if there is a sloping topography, it can just lie along the topography and come back all the way to the ocean surface eventually, just as a result of this mixing profile. So it looks like now we have sinking in the interior, but waters can still rise along the boundaries. That seems to change a bit the distribution of the circulation, or what is the effect of mixing in the ocean bottom. Notice that here I keep insisting that waters can rise along the boundary. It doesn't mean that all the mixing is right along the boundary. Actually, we can define 2 regions. This is again our topography. There is what we would call in GFD, or fluid dynamics jargon, is the bottom boundary layer where waters can rise along the boundary. This is the region where mixing is only felt from the top and not from the bottom. And above it, instead, is what I would call the stratified mixing layer. It's a part of the ocean that has still very strong turbulence. This is the turbulence that is generated by waves that break in the stratified interior. Here, the ocean is still stably stratified. So there is strong turbulence here, but this is where the turbulence is increasing towards the ocean bottom. So the profile of mixing, or of the buoyancy flux, strictly speaking here, it's increasing towards the ocean bottom in this layer. This is where turbulence is getting stronger and stronger as I approach the bottom. But then, as I get into this boundary layer, buoyancy flux has to go back to zero, because at some point right through the ocean bottom there cannot be any buoyancy flux, so there could be some geothermal heat flux that would actually make this profile even a bit negative. But that's a small correction. It's just telling you eventually it has to go to zero because there is no mixing through the ocean bottom itself. We can actually estimate how much water is rising along the bottom boundary layer if we just know what is the divergence of this buoyancy flux. If the buoyancy flux is negative, this term is negative, and just by knowing the buoyancy flux, I can tell you how much water is crossing these two density surfaces. They are flat in the stratified interior, and then they become normal to the boundary. In the boundary layer, they had to become normal because I have no normal and no flux boundary conditions, so I cannot have density gradients into the layer. But all you really need to remember about this equation is that if I know the buoyancy flux and the stratification of the ocean, I can estimate the rate at which water sink in the stratified interior, and I can also estimate what is the buoyancy, what is the amount of water rise across density surface in the bottom boundary layer. The bottom boundary layer is the place where the buoyancy flux now increases with height. So this term is positive, so the water is actually going up. So you can formally derive the equation that control that profile. So now, let's take a face value. It looks like there is a difference, or it looks like because of that buoyancy flux profile, we can have sinking of waters in the ocean interior rising along the boundaries. Now I want to go through 3 steps. The first one is, can we actually see a solutions like that in a pretty idealized but reasonably representative simulation of a global ocean? So is something like that really occurring? And if it does occur, how does it look like? And then we can move towards actually seeing whether we have any observational evidence of anything of this happening in the real ocean. So very quickly, what we want our simple idealized simulation to do is to represent that overturning, the abyssal one, not necessarily the upper one that we said instead doesn't require much mixing. This flow is mostly along density surfaces. Paolo Cecil has written a number of great papers about that cell. That's not what we want to think about right now. This cell is primarily confined to the Atlantic, so what we're trying to do is an idealized version of the Pacific, so we completely forget about that upper circulation. And we want a Pacific Ocean-like simulation that is connected to a channel. The reason why we want a channel, you remember that circulation is fed by convection around Antarctica in the Antarctic Circumpolar Current, which is a current that flows all around the globe, south of Australia, South America, and Africa. So this is the idealized model that we are going to use. This is the bathymetry of our model. So this is a reentrant channel to the south. This is the continent. This would be Antarctica. And this is our basin. Now, Rick Salmon is in the audience. So when he started teaching us fluid dynamics and the circulation of the ocean, we spent the first number of weeks discussing square basins. So they're basins that have vertical lateral walls. And indeed, this is what typically idealized model of the ocean circulation tend to be when people want to look at idealized configuration. I'm guilty of having used model of that kind. Paolo Cecil would be another example of a person guilty of playing with those kind of systems. And I remember that indeed Rick Salmon at that point warned us that those were very idealized systems. So one day on the lecture he shows up, finally look at a realistic simulation, and therefore the bathymetry is going to be parabolic. So this is a realistic simulation of the ocean because I'm using a parabolic profile I was advised to do. But this is going to be important. The fact that we have a parabolic profile is crucial because I said that this rising of water along the boundary requires a sloping boundary. If I had vertical walls, you can start thinking in your mind what you think might happen in this simulation as I go along and explain what I'm going to do. So the next thing is this is the bathymetry. I'm going to feed it with water. I'm blowing a wind at the surface just in the Southern Ocean that will accelerate a current in the Southern Ocean. I'm going to restore at the surface to very cold temperatures over my Southern Ocean, so that will drive convection, like we said happens in low latitudes. And instead I restore to a uniform temperature over my whole basin, which is a representation of my Pacific basin. That way there is no convection in northern latitudes here, like in the Pacific Ocean. That is definitely an idealized simulation. It just to give you a bit the flavor of how you force it. But you would expect in a zonally average sense, if this is the South Pole, North Pole, and depth, that you're going to have some convection of water along the southern boundary that flows in the interior and then rise back up. So an overturning a bit like what you see in the Pacific. Now the other thing that we do very different from the typical idealized experiment that people do in this kind of situation is that we're going to provide them, to prescribe the mixing profile. So I'm going to prescribe in this simulation the buoyancy flux, which is not quite what you generally do. So we have a buoyancy flux, so we're going to solve an equation for density rho dt, which is forced by a buoyancy flux or my mixing profile that increases towards the ocean bottom, and then in a boundary layer of 60 meters or so, it goes back to 0. So what I'm doing is, I'm not contending that the mixing profile is generally independent of density stratification, which is what I'm imposing here, but I'm just asking, well, I want to see whether if I prescribe the mixing profile observed in the real ocean, can I get a stratification and overturning consistent with what happens in the real ocean? I'll contend you, and again, keep thinking that if I had vertical walls, that would not happen. I would have serious problem on getting a solution that looks anything like the real ocean by prescribing that mixing profile, even though clearly my theory should be a theory that explains the stratification of the ocean, its overturning, and the mixing profile that is observed. If one of the three pieces is missing, meaning that theory doesn't apply to the real ocean itself. So now let's look at the results of that simulation. So this is depth from the surface down to 4 kilometers. South Pole, North Pole. The black lines are density surfaces. So you see this is a zonal average. You see that this ocean is stably stratified like the real ocean. So this idealized simulation is capturing the fact of stratification. And the contours are describing the overturning circulation. We have sinking of water at low latitudes, rising up and coming back and closing the loop, the maximum in the overturning of order 10 Sverdrup or so. So that solution has the mixing profile that I impose consistent with observation, and also has consistent with observation a stratified interior and overturning that looks a bit like the Pacific one, at least qualitatively. So now we can analyze this solution to see whether, indeed, because I prescribed the mixing profile I just told you, with the same mixing profile as function of height above the bottom, what does the velocity in that simulation look like? And here we're looking at a few sections at a few latitudes. So these are longitude, depth section, or the vertical velocity itself. Wherever you see blue, it means that the water is sinking towards the ocean bottom. When you see red, it means that it's going upward. So you see in all of these sections, you mostly see blue in most of the ocean interior. So that is telling you that indeed the water is sinking towards the ocean bottom in response to the mixing profile I'm prescribed. But if you actually look carefully and you squint, there is a red stripe in every section just along the boundaries. So that tells you that along the boundaries, water indeed is rising consistent with the argument I've given. If you want to remember one figure from this whole story, and this is the one that we were very surprised the first time we plotted, but in hindsight is what you expect to see in this system. Now I can plot the amount of water that is crossing a particular density surface. And in particular, I can plot in red how much water is rising across this density surface in the boundary only. And in blue, instead, I'm plotting how much water is sinking in the interiors towards the bottom. So now you see that there are of order, let's take this density surface, 28.2 kilogram per meter square, which is pretty much this density surface is crossing the maximum in the overturning. There are 30 Sverdrups of water sinking through this surface down in the interior. 30 Sverdrups of water rising through this density surface along the boundaries, but there are 30 Sverdrups of water sinking above the boundary layer towards the bottom. The difference between the two is indeed of order 10 Sverdrup, which is that overturning. But what I'm telling you is that when I look at the zonally average overturning, I'm taking an average between a lot of water rising up and some water sinking down. Those 10 Sverdrup is the water is rising up, and that water is indeed balancing the amount of water that sinks in the interior, but it's a very small residual on much larger transports. So the first thing you say, okay, it's an idealized simulation. Now you explain me in theory why that should happen. You've run a simulation that essentially was imposing that result. Does that have anything to do quantitatively with the real ocean? And I can answer that, or can try to answer that in a couple of ways. The first one is try to use scaling arguments, more or less, they're not much more than that, to understand what are mixing profiles in the global ocean and what numbers are we talking about in terms of amount of sinking or rising in the global ocean. So what we've done here, and I won't spend much time or elaborate because it's still really at the level of a hand-waving argument. What we can do is, as I said, that we know that what is generating all this mixing is radiational waves from the ocean bottom. If you know the bottom topography of the ocean, and we have estimates of that, if you know the bottom barotropic tidal velocities, and we have estimate of that. And from numerical model, we get estimates of the eddies at the bottom of the ocean. We can just estimate from linear wave theory how much waves are generated from the ocean bottom. So that part is reasonably well done. Bill Young has worked some of the most useful formulas to do this kind of exercises for the tidal part. In any case, we can estimate, this is work we've done with a student, Max Nikurashin, when he was formerly at MIT and continued afterwards. So we can estimate how much waves are generated from the ocean bottom. Now, if we assume that a maximum of 30% of those waves actually locally break is very close to where they are generated, this is some average number, it's very uncertain, and we could also discuss how sensitive the results are to that. But more importantly, then we prescribe that the amount of waves that break, they mostly break close to the ocean bottom, and then less and less as you move upward, so you get the density flux profile that is decaying towards the ocean surface. So, and you use e-folding scales that are based on some of these HRP profiles that have been collected across the oceans. So now you have at every point in the ocean a full vertical profile of the buoyancy flux by just using linear wave theory and assuming that 30% of those waves actually break towards the ocean surface. And then, of course, you impose that the buoyancy flux goes back to zero in a bottom boundary layer. If you use that estimate, you remember by knowing the buoyancy flux profile, the rate of mixing profile, and knowing the stratification, I can estimate the amount of water that is rising along the boundaries and the amount of water that is sinking in the interior. And this is the picture I'm showing here. For a few density surfaces, notice that I always look at pretty dense waters because we are still addressing the question, what is the circulation of that deep overturning for densities higher than 27.5 or so kilogram per meter cube. Again, let's look in particular at 28.1. That is the density surface that separates what are called Antarctic bottom waters and North Atlantic deep waters, the very deep waters around which that overturning, blue overturning circulation was spanning around, so it's close to its maximum here now. This is the same overturning circulation I've shown you before from the North Pole to the South Pole, but instead of using density as the depth as the vertical coordinate, I'm now using density, so it's the same Lumpkin and Spear plot. But now we are looking at density close to this 28.1 or so, the maximum of that overturning of this big cell here. Well, now again, so we're looking across this density surface. I'm showing that while we have of order of, let's say, 30 Sverdrups of water rising along the boundaries across that density surface, but there are about, 25 Sverdrups sinking down. If you take the difference of the two, let's say that this is 30 to 35 to 25, differences of order 10 Sverdrups. So again, also in this case, you have much more water rising along the boundary than sinking in the interior. That difference, 10 Sverdrups, is of the order of magnitude of this overturning at that maximum. But it's again the difference between a lot of water rising along the boundaries and water sinking in the interior. So that at least tells you that for all we know from simple scaling argument about ocean turbulence, it's that picture that I'm showing you in the idealized simulation is consistent with what we should expect for the real ocean. But it's by no way a proof from first principle from observation that is what is happening, because it's still a pretty indirect inference. So now we can try to move a bit further in trying to look for observational evidence. And this is as far as we can get at this point, but I'll show you how I think we can do better in the future. And here I'm going to look at results collected as part of the DIMES, diapycnal and isopycnal mixing experiment in the Southern Ocean. That was the same experiment that I used to show some of you of the vertical profile of mixing all the way to the ocean bottom from Drake Passage. That experiment, masterminded by Jim Ledwell in Woods Hole, who is an expert of releasing tracers in the ocean interior and measuring them at very low concentration. That experiment consisted of releasing a tracer where there is this red dot. This is a sector of the Southern Ocean. This is South America and the Antarctic Peninsula. So we are in a place where there is the strong Antarctic circumpolar current going from left to right here, blown by the winds. What Jim Ledwell did at this red star, he injected a tracer at 1,500 meter depth. An anthropogenic tracer, it's a sulfur pentafluoride. It doesn't matter what it is, but what matters is that he can measure it at very low concentration, so he can measure it for a very long time, as this tracer is advected by the current from where he injected it at 115 west or so, and went all the way. He can track it as it gets advected by the current from where it's injected all the way through Drake Passage and east of it. And he can also measure how fast it spreads across density surfaces in the vertical, which is what we're going to care about because this is what the focus is in this particular talk. And I'm going to show here that now this is a plot, this is again depth. Well, depth, yes, and this is the concentration of tracer. This black line is what was the distribution of tracer when it was injected here and actually sampled along all the points along this black line. So this was pretty confined along a particular density surface where he released it. So it was very confined where it was injected. They tried to be very close to target density surface. And then as you let it go, it starts spreading out across this density surface as a result of all these breaking gravity waves that try to mix across the density surface itself. And so he measured it again when the tracer arrived through this transect D right at Drake Passage. So it's going from here to there. And sector D, the tracer is a bit more spread out than it was originally. This is much more confined along this target density surface, while the second profile is a bit more spread out. So the breaking waves have started spreading it out through mixing. You can estimate the rate of mixing if you know the spread of these two distributions, the black one and the transect, D is the red line. So I can take just the width of that distribution, square minus the width when it was injected, so the red minus the blue, divided by the time it took the trace to go from here to there, and I have a 1/2. This is an expression due to G.I. Taylor. This expression that is just based on measurements of the tracer gives me a turbulent diffusivity across the density surfaces, and for this particular two transect gives me a value of 2 × 10⁻⁵ meters squared per second, or an order of magnitude smaller than the value that we've been discussed that Walter Munk seemed to have inferred for upwelling of waters from the ocean abyss. So it's a region where mixing is pretty weak. That's not a terrible surprise in inside, because if you look at these maps that I was showing you before, you see all these wiggly lines. That's the topography, the ocean bottom. This part of the ocean is incredibly flat. And we said that the waves are mostly generated by flows flowing over uneven topography. So there is no uneven topography, so not much mixing to drive it. But now we can look what happens when the tracer go from sector D to sector F. So now we are past Drake Passage, and now we are on very uneven topography. So you go from red to green. You see that all of a sudden these two transects are pretty close by together. It just doesn't take even all that much to cross that distance. The tracer moves pretty fast from one to the other, but the tracer all of a sudden spread out quite rapidly. You see that the green profile, which is, well, what is the brown profile, which is this sector F, is much more spread out than the red one that was still pretty pointy. Indeed, if I use Taylor's formula and I take the difference between the width squared of the red profile minus the width squared of the brown profile, and again my diffusivity, I get something that is 30 times as large as what it was upstream of Drake Passage, or maybe 10 times as large. Now it's 30 times 10⁻⁵ meters squared per second, or 3 Monks. Now all of a sudden we have numbers that are even larger than what Montemark might have inferred. So the mixing here was definitely much larger. So we are entering in a region where it seems like there is a large radiational waves and substantial breaking. So now you could think, well, now you have a direct estimate of the mixing. We also had some vertical profiles of turbulence. Maybe you can just try to use the tracer and see, is it true that the tracer seems to rise along topography, along the boundaries, and sink in the interior? And, well, you would have to sample very carefully along the boundaries to do that, and that wasn't done as part of this experiment. You see, these are all the profiles that were taken. So we can't directly from the experiment look where the tracer is going. I'll come back in a second. I think it could be done. It just wasn't done here because it wasn't the focus of the experiment. But we can do something, or at least we can try to be a bit more creative and just use the observations together with the numerical model to see whether we can interpolate in the regions where we didn't have the observation. So what we've done here, we are running a high-resolution simulation of a patch. This is again the South America, and the Antarctic Peninsula is somewhere down here. So we are configuring a patch just in the region where we run the DIMES experiment. The model is, what is it? It's 5 degrees in latitude, and of the order of 14 degrees in longitude. And it's forced at the boundary with a larger scale model that assimilates observation, so it's constrained to observation. So the model at the boundary essentially is fed the hydrographic structure of the Southern Ocean. So on the large scale, the model is going to be very accurate because it's restored, essentially kept on track with the large observational structure. But the model is run at a 500-meter resolution, so it's a very high horizontal resolution at 100 vertical levels. So it generates the current itself that enters here, goes barocritically unstable and generates all the lateral turbulence that you might expect to develop in a system like that. So it does give us more realistic representation of what is the flow that the tracer must have experienced. At this resolution, we still don't resolve gravity wave breaking, which I said is what eventually drives the mixing. So what we've done instead, we prescribe a profile of kappa in the numerical model that is based on HRP profile, high resolution vertical profiles, direct measurements of mixing that we have in this part of the ocean. You can get profiles of kappa from those measurements, and those measurements were collected wherever we have white dots or black dots. So in this area, it's pretty well covered. And we found out that the profile of kappa as a function of height above the bottom is quite similar in all of these profiles. So we can just use this kappa profile that goes from 10 to the 3 meters squared per second all the way down to 10 to the minus 5 meters squared per second, 2,000 meters above the bottom. So we prescribe a map of kappa everywhere as a function of height above the bottom. It's largest towards the bottom, decays upwards, like we said, the observations tend to suggest. And now we can inject the tracer up here where the tracer enters in these transects in the real observation, and we're going to inject it with the same distribution as the observed tracer, and then we let it be advected through the domain until it exits from the other side. And since in the numerical simulation we are prescribing a profile of kappa, we expect that this tracer injected with the same distribution and on the same target density as a real tracer will spread out in response to that mixing. And let's see if I can play a movie. So now in this movie, the tracer is injected back here. This section here is in the back here, and it's coming towards us. So it's exiting from this side, and you see that the tracer gets spread laterally very efficiently by the vigorous lateral eddy field. But at the same time, with this resolution, definitely you can't see it, but it's getting thicker and thicker because it's being spread across density surfaces by that vertical profile of mixing that increases towards the ocean bottom. Now, the first thing we wanted to know, can we use this model to do anything useful, meaning in what sense it's consistent with the observational evolution of the tracer that we have. So here I'm showing you this is density, and this red line is the distribution of tracer as measured in the transect D upstream as the tracer entered in direct passage. The black dots are the individual measurement. The red one is the average of the measurement. That's what came out of the observation, and that's what we use as the initial condition for the model. Now, the next two profiles is, well, this is from data, and you see how much the tracer spread out by the time I go to transect F after it experienced the mixing as it's coming out of the integration domain. So this is the observed one, and that's what I use to estimate the large kappa that I've shown you before. It's spread going from here to there across density surfaces. There was no tracer up here, now there is tracer up there. Now this is the same profile from the numerical simulation. They're very hard to tell apart. Again, the dots are the measurements exactly where they were collected during the experiment itself. So that is telling us that just using that self-similar profile of kappa then can look suspicious, but actually any test you do, you have a hard time to convince yourself that there is any difference between these profiles, even in terms of their skewness, which is something that Jim Gladwell is particularly keen on. But what it's telling us is not that the model is perfect, but that the model, with that by using the prescribed profile of kappa from the microstructure measurement, does reproduce the spreading of the tracer across density surfaces. So it's useful to start looking at the statistics of the tracer. One of the things, for example, that wasn't clear is that, can I ask how much time do I have left? So 5 minutes. So I should be careful about, I'm nearly done. But something that I'm not discussing here, and I'm very happy to discuss it later on with people, is that as part of this experiment, one of the puzzles were that the tracers seem to spread much faster across density surface than individual measurements at the depth of the tracer, individual measurement from HRP profile suggest that they should. So there was this puzzle, and that's something we are working on. But what it's telling us, the model can be used very effectively to understand where that difference is. Indeed, I'm using a model where I prescribe the mixing profile that were measured in the ocean, and then I just inject the tracer, I look at what rate the tracer is spreading. The tracer is spreading at a rate which is much faster than would be expected from the measurement turbulence at the level where the tracer is. And it has a lot to do with the fact that the tracer keeps encountering topography laterally at that depth, and those places disproportionately dominate the mixing. Just to show you that if we have a number of independent line of evidence to show that the model is actually able to reproduce the rate at which the tracer spreads in the vertically, and that has a lot to do with the fact that it reproduces the lateral steering by eddies, bringing tracer close to topography. But for what I want to discuss now is that now I'm using this model that seems to have been validated, at least in being able to reproduce the spreading of a tracer, so the distribution of mixing seems to be consistent with what the tracer has truly experienced, and now I can use the model to measure the buoyancy flux. If you have a model, the cap is prescribed, but the density stratification is a result of the model, so the flux is just that diffusivity times d rho dz, the vertical stratification in the ocean. So I can just take the model and look at what the buoyancy flux is. If I have the buoyancy flux, I can estimate how much water is rising along the boundary and how much water is sinking in the interior and respond to that mixing profile that is increasing towards the ocean bottom. The red curve is again how much in this patch of the ocean is rising along, how much water is rising along the boundaries. The blue one is how much water is sinking in the interior, and the black one is the difference between the two, which is the net upwelling of water in response to that mixing. So in the net, the water is again upwells, but all that upwelling is happening along the boundaries. There is much more upwelling along the boundaries than sinking in the interior, even in this small patch. Now, you see that that effect is most pronounced again, this density surface, 28.1 kilogram per meter cube. Again, is the density surface separates largely North Atlantic deep water from Antarctic bottom waters. The tracer that we looked at was injected at 27.9. So in particular, we tried to look directly with the tracer where we could estimate how much rising the net tracer was experiencing. But at that particular density level, the signal is very weak, so you can't directly estimate it. But the model is suggesting that indeed the tracer is indeed responding according to that curve, except that we didn't measure it there, and that's where you would want to go if you want to see the direct upwelling of waters along the boundary. So, just to leave you with something, this is work that we have just submitted for consideration to NSF for a field experiment. The idea would be that we can probably measure indeed the upwelling along boundaries. We have to go to a nice canyon and to a nice bowl-shaped canyon. We want to see a place that has lateral boundaries. This is some work that I'm involved with Matthew Alford over there, Alberto Navera Garabato at Southampton, and Kurt Paulson at the Scripps Oceanographic Institution. And being sensible observation is the first thing they wanted is, since all you care about is some bowl-shaped ocean, we want something which is not as deep as 4,000 meters. If we can lift it up a bit, that's all to our advantage. So the idea is to go to the Rockall Trough, which is just north of Ireland up here, and it's just around 2,000 meters deep or so. So we can do an experiment where we're going to look at the turbulence, upwelling of waters in that bold environment, except that we go deep, but not as deep as the Brazil Basin, for example. We have lateral boundaries, and the idea is, or what we can do is that the first thing is that in all the experiments that Jim Ledwell has done so far, they always try to put the tracer far away from ocean boundaries to look at the effect of mixing in the stratified interior. In those experiments, especially in the Brazil Basin, they definitely saw sinking of tracer, at least in the early phases of the experiment, much along the lines of what I said. That is the response of or at least I strongly believe that that's the response of the tracer to the mixing that it's experienced, that it's increasing towards the ocean bottom. The original papers, they said that maybe it had to do with tracer particle not being perfectly neutrally buoyant. And at the time they believed in that story, talking personally with Jim Ledwell more recently, they tried to repeat the experiment in the laboratory and the waters never seemed to sink by themselves. So they have to believe that it's actually a real physical signal, so it would be consistent with the picture I've shown. But since they never put the tracer along boundaries, they never really were able to sample the upwelling along the boundaries. So here you could just put the tracer first along the boundaries. You should see for a while upwelling along boundaries. Then the part that I never discussed and the one could get into, there is also a lot of lateral steering happening in the ocean. So the tracer for a while will sink along the boundaries, but then it gets affected in the interior. So after a while, you would expect the tracer to start sinking in the interior at the same time as rising along the boundaries. So you really have to start injecting it along the boundaries to see the effect. The second thing that we can do is that we can measure the turbulence all the way into the turbulent boundary layer. That's something that, again, is not done when you are dropping your HRP down 4 kilometers below the bottom, the last thing you want to have is for it to just hit the bottom and never come back. So generally, these profiles are always substantial height above the bottom itself, also because we don't have topographic maps that are that accurate that you want to risk anything within a bottom boundary layer that is typically between 50 and 100 meters deep. The second, more fundamental issue for the people that know the field is that the way the HRP really measure turbulence is to rely strongly on the presence of a background stratification. You use what are called Cox formulas that try to relate the dissipation of kinetic energy to the buoyancy flux, and that works only in stratified environment. When you enter in the boundary layer, that doesn't quite hold, it's pretty unstratified. So if you want to measure profiles in the boundary layer, you have to be a bit more creative, but you have the advantage that there is a solid boundary, so they can anchor system to the bottom, so you can have moorings anchored to the bottom. You could measure directly with ADCP, vertical velocity and temperature fluctuation, and measure directly your buoyancy fluxes, W prime, B prime, or W prime, T prime. And at the same time, you can use the usual microstructure estimate based on Cox-like formula and see to what extent they might or might not apply in a boundary layer. But then again, if you see this profile increasing towards the bottom and then coming back to zero, that's a direct estimate of the water mass transformation. So you should be able to close it, to close the budget and actually show in real action the dynamics that I have described. Here I want to show the people that are working on this problem. Just to conclude, as I said, all I want to say is that I expect to have strong diapicnal welling along the bottom boundary layers and sinking in the stratified interior. The zonally average overturning is therefore of the residual of these two transport, and these two transport by themselves are much larger than the overturning we actually described. These are the people that are working on various aspects of this problem. Alice Mashayek ran master the simulation that you've seen in this talk. With Jorn Karlis, another postdoc at MIT, we are trying to look at the implication of these dynamics for the large-scale circulation. For the people that are familiar with the Stommel-Arons argument, the distribution of mixing and whether your waters are rising or sinking has a lot to do with potential vorticity constraint and the horizontal circulation on the ocean abyss. So that this result that I'm describing have strong implication also on what is the horizontal circulation of the abyssal ocean. Henry Drake is trying to use a combination of semi-realistic simulation with tracer observation to see whether we can actually see in large-scale tracer distribution the effects that I'm describing. That's not so easy as you might expect, because there is always a lot of lateral mixing happening in the ocean that tries to smear out the difference between what happens right along the boundaries versus the interior. Greg Wagner was a postdoc with Bill Young until recently before he left for Africa, but hopefully he'll come back, and his idea is to come to MIT to understand a bit more of the dynamics of the turbulence in the boundary layer itself that I keep invoking being this fundamental driver of upwelling, but I haven't described any of the dynamics. And we're going back to works that were started by Peter Rines and Chris Garrett in understanding in detail how that upwelling really occurs. And this is the end of the recipe or the improved recipe, and these are papers that I'd be happy to share with people where we describe most of what I discussed today. Thank you.
The world is changing. Are there any questions? Oliver.
So then, this seems like a pretty convincing argument, and given that profile of, you frame in terms of flux, presumably that would be considered as well.
Yeah.
So you would get upwelling along bottom manifold. But we also know that the downwelling, in terms of convention, also tends to happen along boundaries. So what's different there?
So that is definitely not driven by profile of mixing per se, right? I mean, at that point, it's convection, if you want, you can describe it. Oh, consistent, it is consistent. Maybe that wasn't clear, right? If I go back to this estimate of overturning, right? The difference between these two curves, these time-sphere groups, is this amount of water that is rising across the global ocean has to match the sinking at high latitude that is probably also happening along the boundary. So the difference between these two terms has to match the amount of convection happening at high latitudes. My impression is always more that it's the other way around, is that if you know the difference between these two, that is going to constrain how much convection can happen along the boundaries along Antarctica, because it's the mixing that is going to constrain the rate of that circulation. It's not the other way around. The stratification will adjust in such a way that this is possible. So the convection will set a lot of the stratification properties. By the way, I still think a very good exercise to understand this connection is that people should still think about the problem of Iranda simulation with vertical sidewalls instead of the sloping walls. What do you get in that limit? But I'm not giving you the answer. You can read it in the paper, it's given. But you should think about it, because then you see how much the convection at high latitude is part of that problem and what happens when you break that limit. Does that answer your question? Not quite. You're not happy. We can continue afterwards. Or you can tell me what you really want to know.
Well, this nice profile of diffusivity versus height above bottom is based on a compendium of many, many extremely radiant irregular profiles taken by people like me over time and put together. And there's a high correlation between this variability and small lumps and bumps in the topography. And I was wondering if there's any concern that if there is a correlation between diffusivity and local slope, it's really that average that matters. And I wonder if these nice smooth slopes combined with nice smooth topography would give a result that's different than the average of very grainy mixing over very grainy topography.
So, in particular here, I'm talking now about the times experiment, where I really tested this more carefully, right? So this is the profile. The black line is the average profile, and you see all the scatter around it because it's an average over all these irregular and very jagged individual profiles, so there is definitely substantial variations. That's why I said that we use essentially numerical simulation as a first step to see whether using this average profile will give me a distribution of tracer or rate of spreading of tracer consistent with what the observation seems to see. And the answer was that yes, you don't really need to have much more information than that average profile because the tracer does spread vertically at the same rate. The reason being that it turns out that the lateral spreading is so efficient across the ACC that every water pass will explore most of the area over a few eddy turnover times, so over time scale of order of 10 days, you explore most of the width of the ACC. I'm not saying that you have mixed properties along the whole ACC, but they are just big swirls, so the tracer has been pretty much everywhere. So I think it's just that the tracer is very effective at averaging up.
Passage is kind of a special spot, though. And,
well,
this is a wonderful experiment, mind you.
So oceanographers always get back to you at that, right? If you look at an experiment and say, oh, well, that's a special experiment.
Well,
it might be.
Yeah, we only go to specials.
We are analyzing right now Brazil Basin, also that is a special place. The same story seems to hold as far as we can tell. I think that yes, going to the rock trough and actually taking the profile of mixing itself and being able to, so there the idea is to not have just one mooring profile, but have a set of them to look at that horizontal variability. The variability is a function of slope, so we are going region of steeper slope, flatter slope, and being able to look very carefully locally how that variability might impact the traces. Something needs to be done, but it wasn't done here to the point that we could test it. I think for the question we done here, the answer was that at least in times maybe the lateral movement is strong enough that that is not an issue. It might be in other places.
Bill, if you do it, if you repeat the simulation with a constant kappa sub rho, is it completely wrong? If you allow me to pick the constant. Like 1 month looks pretty good.
So yes, it depends on what you mean by completely wrong, but for everything I discussed today, yes, it would be fundamentally flawed because what you know is that, I keep insisting that this distribution of vertical velocities,
Well, that's the previous picture, right? That's the comparison.
At that particular level, well, things don't change. At that particular level, the kappa hasn't changed all that much. This thing spreads, what, by 100 meters or so. Over that scale, I can't tell that I resolve any vertical variations.
Right. So I think that kappa will get that answer.
At that particular level. But what you won't get is that if you pick a particular kappa, now you have going to be having uprising of waters in the interior because the stratification is always a minimum in the ocean bottom and increases towards the surface. If I multiply by a constant kappa, I'm going to get the mixing profile increasing towards the surface. So this picture is just reversed.
Okay.
And I think that that is true for any numerical model that uses a constant kappa. Any climate model, large scale model is used. One of the issues that you might argue about is that they're going to get the right stratification, the right overturning, but consistent, their mixing profile is increasing towards the ocean top, which is very inconsistent with everything we can tell from observation about profiles of mixing.
Well, constant kappa does give you the Phillips winch flow along the boundaries, which is going out.
Yeah, but it also gives you a lot of upwelling in the interior.
Okay.
And actually you find out that no, this actually goes down quite substantially because the strength of that upwelling, it's actually the Garrett solution. The strength of that upwelling depends on the kappa right above the boundary, so you have to take this very large value you have at the bottom, that is you get the upwelling. But if you put a constant kappa here, if I go back here, if I use a constant kappa, this is 10 to the 3 meters squared per second, it's an order of magnitude larger than Mach, so I would decrease that transport at the boundary that depends just on kappa above the boundary layer by an order of magnitude. So essentially it disappears, which was part of the reason why Garrett and Rines kept asking why that line of research essentially disappeared, and their claim was at the time they didn't have vertical profiles of kappa all the way to the ocean bottom. When they started putting numbers even as large as the 10 to the minus 4 meters squared per second of Walter, the amount of transport seems to be so small that they decided to drop it because it didn't seem to matter too much in the large scale, but that was before the observations came about. So it's, to some extent, it vindicates those studies.
Also,
Raffaele, I wanted to point out that your kappa of 10 to the minus 4 is not nearly as pretty as our 1 CGS.
But if I call it 1 Mach, then it's as clean as that.
okay, any more questions?
Well, thanks again for a very